Hello guys, I'm Munot and welcome to the School of Physics, and today we are going to start sound waves. So today we are going to complete sound waves in a very few minutes. Okay, before continuing, I'd like to request you all to subscribe to my channel, because then only I'll be more encouraged to make more videos like this, more revision videos. So let's begin with sound waves. So what is sound waves? So we have seen in our last waves in motion chapter that the wave motion, suppose the displacement equation comes out to be something like this: S is equal to S naught sine kx minus omega t. Okay, something like this, or omega t minus kx. So when we talk about this in terms of displacement of sound, this is S is equal to S naught sine kx minus omega t, where if we write it in terms of pressure, we write it P is equal to P naught sine of kx minus omega t, but there is a phase difference which is of equal to the angle pi by 2. So the pressure and the sound have a phase difference of pi by 2. Now what is this P naught? This P naught can be written in terms of S naught as bk S naught, where B is the bulk modulus, K is the 2 pi by lambda, and S naught is the S naught of the equation number 1. So this can be written as P is equal to bk S naught, okay, kx minus omega t plus of pi by 2. So this is the basic sound equations. So we did not do the standing waves in our last chapter. I'll just give you a brief idea about what standing waves are. Suppose we have two equations. Y is equal to a1 sine kx minus omega t. Okay, so y1 is equal to a1 sine of, or say just a sine kx minus omega t, and we have a very similar another wave which is running in exactly in the opposite direction. It has the same amplitude a, same k, same omega. So y2 is equal to a sine kx plus omega t, just the direction are different. So when both of these superimpose, y1 plus y2, then this equation comes out to be a standing wave equation, which is equals to 2a cos kx sine of omega t. So as we can see, this 2a cos of kx makes the amplitude. This 2a cos of kx makes the amplitude, and then it is also a sine equation. So this is the amplitude. So here we have, say, amplitude equals to 2a of sine of, cos of kx. The amplitude equals to 2a cos of kx. So we have a node here. Now this is the sine equation. So this part is called a node. This is called an antinode. This is again a node, and then this is an antinode. So like this we have nodes and antinodes. Now I'll tell you very simple and shortcut formulas. These are invented by me for resonance, for vibrations inside an air column. So very simple, very generalized formulas. You won't find them anywhere. You'll have to learn 15 different formulas. Rather, what I did is, by my observation, I converted it into one or two single formulas. So a very important chart, pay attention. Okay, so first of all we write mode. Okay, so case one, when both the ends are closed, or open, closed or open. Okay, so what happens in this case? If the mode is, say, first mode, then the overtone is fundamental. Okay, fundamental. If the mode is second mode, the overtone is first overtone. If the mode is third mode, then the overtone is second overtone. Okay, so similarly like this, if the mode is n, then the overtone is n minus 1. Okay, this is how mode and overtone goes hand in hand. Now the next thing that I come is mode, overtone. This is called harmonic. Okay, this is called harmonic. So if the mode, when both the ends are closed or open, when both the ends are either closed or open, then if the mode is n, then the harmonic is also n. Then antinode and node. Antinode, the next thing that we come see is node or antinode. So node or antinode. So if both the ends are closed, then node is n plus 1 and antinode is n. If both the ends are open, then node is, number of node is n and antinode is n plus 1. Next thing, very important thing that we are going to see, it is 2L by harmonic. We have to remember it like this: when both the ends are either closed or open, we have to remember 2L by harmonic is lambda. So harmonic was n, so lambda will become 2L by n. Lambda will become 2L by n, and the frequency will become velocity upon lambda, as you know, will be equals to v upon 2L into n. So this will become of frequency. And what was velocity? Velocity we knew was under root of t by mu, where mu was mass per unit length, mass per unit length. Okay, where mass was in kg. So this is mass per unit length. V is equal to under root t by mu, frequency v into n upon 2L. Lambda is equal to 2L by n in the case when both the ends are closed or open. Okay, have a look, very important thing. Now after a few seconds we will move on to the next formula. The next formula, when one end is either closed or open. Okay, or one end is closed. Okay, so we move to the next thing. I'll just keep it written, fundamental first. Okay, I'm deleting all this. So when one end is closed or open, we just have to remember what is different. We have to remember that one thing that is different will be, this is not 2L by harmonic, lambda will become 4L by harmonic, and the harmonic will become 2n minus 1. The harmonic will become 2n minus 1. So if the number of modes is n, if the mode is n, then the overtone will be n minus 1, the harmonic will become 2n minus 1, and lambda will become 4L by harmonic, that is equals to 4L upon 2n minus 1. When this case is, when one end is, case number 2, when one end is closed. Okay, when one end is closed. So n minus 1, harmonic 2n minus 1, nodes and antinodes will be same in both the cases, which will be equal to n, and frequency will be equal to v upon v, where v is equal to under root t by mu, as we have written, where v is equal to under root t by mu, v upon lambda, where lambda is 4L into 2n minus 1. Very important, very simple formula. We just have to remember 4L by harmonic, and harmonic is 2n minus 1 in the case when one end is closed. Have a look at this. This is very important. Okay. The next thing that we are going to see is resonance. So in resonance, what happens is, the first resonance happens at a distance of lambda by 4. The second resonance happens at a length of 3 lambda by 4. So L2 minus L1 is equal to lambda by 2. This is all that we have to remember in case of resonance. Okay, so in case of resonance, first resonance happens at this, which is at lambda by 4. Okay, second resonance happens at a distance of, say, this. Okay, so second resonance happens at 3 lambda by 4, 3 lambda by 4. So this is length L2, this is length L1, and we can write L2 minus L1 is equal to lambda by 2. Okay, so this is what happens in a resonance column. All that we have to remember. Okay. The next thing that we are going to see is constructive and destructive interference. So now we are going to talk about multiple sources of sound waves. So suppose we have a source S1 and then we have a source S2, and this is, say, the part distance of a, so this is the listener, okay, so this part difference is x1 and this part distance is x2. So suppose both of them are moving, at different distances from the listener. So when x2 minus x1 is equal to lambda, n lambda by 2, okay, when x2 minus x1 is equal to n lambda, not n lambda by 2, n lambda, then this is a constructive interference where you'll hear a maxima, when x2 minus x1 is equal to n lambda. Okay, then when x2 minus x1 will be equal to 2n plus 1 lambda by 2, then this will be a destructive interference, and so this is called the part difference. So this is 2n plus 1 lambda by 2. This will be a destructive interference, and here you will hear a minima. Okay, and how many maxima and minimas will you hear in 1 second? Suppose the frequency of this source is f1 and the frequency of this source is f2, then the number of maximas and minimas that you hear in 1 second is called beat frequency, which is equals to f2 minus f1 is equal to the number of maximas and minimas that you hear in 1 second. And what is the timing of beat? So between every 2 consecutive beats, that is between every 2 consecutive, say, maxima or minima that you hear, the timing is called beat frequency equals to 1 upon f2 minus f1. So this is called beat frequency. Okay, now we cover the next thing that we are going to cover is a very important topic, and it is called the Dopplers effect. Okay, so I guess constructive destructive interference is clear. N lambda, 2n plus 1 lambda by 2, beat frequency f2 minus f1, and so beat time period between 2 beats 1 by f2 minus f1. Okay, next thing that we are going to cover is Doppler's effect. What is it? It is Doppler's effect. Now what is Doppler's effect? So suppose this the speed of sound in normal medium or in the medium, speed of sound is s. Okay, and this is the speed of the observer, the velocity of sound is normal medium is v, and this is the velocity of observer, and this is the velocity of source. So if the observer and the source are moving towards each other, right? If the observer and the source are moving towards each other, then I'll okay, so so there will be a change in frequency. So that frequency is what we write as Doppler's effect is equal to f dash is equal to v plus minus v observer upon v plus minus v of source into frequency that was normally there. So plus is when the observer is moving towards the it's moving towards the source, and minus is when the source is moving towards or away from the observer. So when it is moving, observer is moving towards the source, then this will be a plus. If the observer is moving away from the source, then this will be a minus. If the source is moving towards the observer, then this will be a plus. If the source is moving away from the observer, this will be a minus. Okay, so this will be the change in frequency. So this is the new frequency, this is the old frequency. Okay, now this VO and VS, this VO and VS should be along the line joining the source and the observer. I'll give you an example, very good example this is. Okay, so suppose this is the observer moving in a direction this and at a velocity VO. Okay, and this is at the 90 degree, say this is 90 degree. So this is not a straight line, one second. This is so here we have the source moving in this direction. Suppose this is 30 degrees, and then this becomes 60 degree. So we have to write the Doppler effect for this thing. So Doppler effect, we have to see the velocity of observer and the velocity of source in the direction of the line joining the source and the observer. Very important, listen to it again. In the direction joining the line, in the direction of the line joining the observer and the source, which is the line that we have drawn here. So for this, if we have to write the Doppler effect, we write V F dash is equal to V, which is the velocity of sound in this medium, plus, because it is observer is moving towards the source, and this we will write V naught cos 30 degree, V naught cos 30 degree, V naught cos 30 degree, or V observer cos 30 degree. Then this we will write, since the source is also moving towards the observer, but we'll have to see the direction of motion, velocity of the source along the direction of the line joining the observer and the source. So here along this line, this is Vs cos 60 degree, velocity source cos 60 degree. Since the source is moving towards the observer, this is Vs cos of 60 degree into frequency f. So this is how we write the Doppler's effect. And Doppler's effect is one of the most important questions that is going to be asked in your either board exams or your objective exams. So the concepts should be crystal clear. There should be no confusion. The velocity of the observer and the source is seen along the line joining the source and the observer. So guys, this was my lecture on sound waves, and I hope it is very useful to you. And just keep on revising the formulas, you'll do well in the exams, and please subscribe to the channel so that I make more videos like this. Thank you so much for watching.